So this is Urysohn Lemma, Russian guy. So what we're gonna say is, well, so it's called a lemma now, but it's only called a lemma now because we just use it for other results. But it's not a typical lemma, as it doesn't really play nice. Let X be a normal space, and then if we're gonna let A and B be disjoint closed subsets of X. And then we're going to choose a closed interval AB. The closed interval in the real line. Then there exists a continuous map. Continuous map that's going to take my space X onto the closed interval or into the closed interval such that f of X will return A for all points X that are in A, and I want f of X to return B for all points X that are in B. And then what we're going to conclude, if we're able to show this, what we're saying is basically existence of a separation function. So normalcy, you can separate disjoint co-subsets. So it's kind of an outline of a proof. So we need only consider the case where the interval um, general is follows. The nature of how we do the construction will make it so that it really ultimately doesn't matter what we have, so we just choose rationals to start. So we first are going to use the normalcy. So normality to construct a certain family of open sets. We're going to call them U sub P. Open sets of X. Indexed by the rational numbers. Then we show, well, we use these open sets to define the continuous map F. So this isn't really part of the proof, but it's just kind of like, this is big picture. So the first step before we can even get to the continuous map stuff, and as a means of review, so that at least it makes sense what's happening. In topology, continuity has a slightly different definition. We're basically saying if I have an open set in the range space, and I take its inverse image back into the domain space, that inverse image also needs to be open. So if I go from open in the range space to open inverse image, and if that's true, then you have a continuous map. So that's why we're interested in first defining open sets, because if we're able to index open sets for all of the points in the topological space and take it into 0, 1, and then we're just basically going to then the selection of the rationals is going to allow us to always be able to choose open sets and in R that are open, then again that have neighborhoods that are open in the topological space. This is an overview of what the strategy is.
So, since I a little late, can I just verify? Is the objective to have two sets such that all the elements of the first set go to the first endpoint and all the elements of the second set lead to the second endpoint?
Yeah, suppose you have a space, right? So we're claiming that this space is normal, and normal has the property that no matter how I choose closed sets, closed subsets that are disjoint and contained inside of the space, that there will always exist open sets that contain these closed sets, that these open sets themselves are actually disjoint still. So what we're going to say then is this kind of topological property of being normal then is going to imply that we can always define some sort of a continuous map, or I can take points in this space onto R, some sort of a closed A to B, where here's say A, here's say B. And so what it really means for these to be then closed and disjoint from each other or normal is if I select all the points that I could choose that are inside this closed subset, I can just end up assigning them to A, and all of the stuff that's all the points that are contained inside of this closed set, which is disjoint, you can end up assigning to B. So there's this complete separation of the points in these closed subsets, and that's just a restatement of what it means to be normal. So that's what the lemma is about. It's basically saying that those two ideas can be considered equivalent. So separating a function through f and having open sets that contain the disjoint closed subsets.
So to be clear, does this F also need to be continuous for calculus purposes or an analysis? Like, if you were to have some line, I guess, that connects from A to B, would it be continuous line from A to B in reals?
We happen to use closed set of reals for its topological properties, because we know that the rationals are dense in R. So it's more just it's a convenient choice so that we can invoke there are choices that we make in how we select things in the proof that really only work if we're talking about R. So it's well ordered, and we're going to use the ordering of R. That we didn't have to use R. It could be really set that is you can take closed subsets of an ordered set under an ordered topology. But there's no reason to abstract it that hard when you can just do R, since we've already proved that they're the same thing. Yeah. Okay, so let's construct these open sets. Let P be the set of all rational numbers in the closed interval from 0 to 1. Now, I will make a note here so that this choice is not necessarily seen as like the only way you could do this. Any countable and dense subset of this closed interval works. So we're choosing rationals for convenience. So we define for all of the rationals P in P, and open set u sub p of x in such a way that whenever I have p less than q, we have that the closure of up as a subset of uq. And we're going to see this as a relation property that we'll generalize later. So thus, the sets up will be simply ordered by inclusion in the same way that their subscripts, which are rationals, are ordered by the usual ordering in R. What's the usual ordering in R? Just less than. So 1/2 is less than, 5/6, and things like that. Okay, so because P is countable, we can use induction. Define the sets UP. It's technically recursive definition, but it's just way too pedantic for what we need to be doing here. So arrange the elements of P, which are these rationals in 0 to 1, in an infinite sequence in some way. And since it doesn't matter, we'll choose for convenience. We suppose that 1 and 0 are the first two elements of the sequence. So now we can define the sets UP as follows. So we'll first define U sub 1, so the first open set here, as being the complement x minus b. B is closed, definitionally open. Second, because A is closed, because A is a closed set contained in this complement, what's the last question? In the open set to U1. So the idea is, imagine this entire time you've got that A and that B, they're closed, they're disjoint, they don't have anything in common. We have normal. This is open because this is closed, but if you're only taking out, basically you're poking a hole and you're chopping out just B, everything else is still there, including the A stuff, which was disjoint originally. So this is just a state restatement of the fact that we know that A is going to be hanging out in whatever's left over in that open set. Okay, doing that open set U1, we may, by normality of x, choose an open set. Choose an open set U 0. So the first two rationals in the sequence is 1, here's 0. Such that the closed set A is a subset of U0, and we want the closure of U0 to be a subset of U1. In general, we're going to let P sub n denote the first, the set containing the first n rational numbers in sequence. And the idea with the inductive step is if it's going to work for Pn, and then we have it work for Pn plus 1, then since it's countable, it's going to go all the way through for all of B. Suppose that U sub P is defined for all rational numbers P belonging to this finite set P sub n, where we're satisfying this important property that we will see quite often here. And where it's said we don't have to rewrite it over and over again, we'll denote it with like a star in parentheses. And that property is that if P is less than Q, if this rational number is less than this rational number, then I want my open set so that I take UP. If I close that, that should be a subset of UQ. Okay. So we've taken a specific subset of rationals, restricting it to the ones contained inside of 0 to 1. And then again, since we want to be able to define open sets for every single one of those rational numbers, we got to do that through induction because it's countable. And the way we're going to set up that induction hypothesis, we'll start with just a finite set by taking a sequence and then only selecting the first n of that sequence. And eventually, since we can knock down all the dominoes, then it'll be true for all the rationals in 0 to 1. So let R denote the next rational number. Next rational number in sequence. We wish to define U R, so this open set. So consider the set Pn plus 1. So here's where induction comes in. All we're going to do is we're going to take the previous Pn and add the element. So the union of the element R with Pn. And it is a finite subset of the interval 0 to 1. And as such, it has a simple ordering derived from the usual order relation. The usual order relation. And we can see something nice and familiar here. Less than on R. In a finite, simply ordered set, we proved last semester that every element other than the smallest and largest, so other than the smallest and the largest has an immediate predecessor. Oh wait, I don't know how to spell predecessor and an immediate successor.
Sort of just stating the obvious.
You gotta write down the notes, everything that you use.
Right. It's kind of like showing the pay when you're doing your taxes. Like, isn't it obvious that I had a job? Yes, but I got it, here's the receipt. And actually this result's really interesting because I thought it was gonna be obvious, and then when you go through it in the generalized ordered relation, so not necessarily less than on R, there are some things you gotta take into account. So it is obvious, but it's not trivial for this property.
Okay.
The port to this here,
So
to note it on the way.
the number 0, we have numbers in this proof, it's crazy, is the smallest element. And try to see where this is going. And 1 takes care of the largest. 1 is the largest element of the simply ordered set. Simply ordered set Pn plus 1. And so that's kind of nice by construction because that's guaranteeing that R can't be the smallest or largest. So it will have its immediate predecessors and successors. Okay, so where am I here? And R, right, so R is neither 0 nor 1. So thus, R has an immediate predecessor as an immediate predecessor. And we're going to call the predecessor P in Pn plus 1. And an immediate successor. And we're going to call him Q in Pn plus 1. So the sets U sub P and U sub Q are already defined.
I still don't really understand the use of P very well.
It's an open set that is defined based off of the rational number P, which is in the subset 0 to 1 in R.
Wait, so use of P is in R? I thought it was in X.
Well, yes, you're correct. U sub P is a subset, is an open subset of the topological space X, but the P, that index, is in where we're going in the interval. So it's a little bit, yeah.
So you're gonna use that as the
We're using this to guarantee the existence of open sets for like index open sets for all of the points inside of the closed set A.
oh
Yeah, that's what we're building up to. Okay. So the sets are already fine, and we have earlier we talked about we showed that the closure, well, we didn't really show, we just defined this how it's gonna be. Closure of P subset of UQ by the induction hypothesis. So that's the property that we're taking. So using normality of X, we can find an open set. Open set U sub R of X such that the closure of U sub P is a subset of U sub R, and the closure of U sub R is a subset of U sub Q. We assert that the property star now holds for every pair of elements of P n plus 1. And if one of them is R and the other is a point sub S in P sub n, then either we have S being less than or equal to P, in which case we just have that the closure of U sub S is contained by the closure of U sub P, which is contained by U sub R, or S could be greater than or equal to Q. So think of R as being sandwiched between P and Q, and then if you have something that's less than, it'll be less than the immediate predecessor and then pass to the immediate successor. And in this case, the closure of R would be contained by U sub Q, which is contained by U sub S. Thus, for every pair of elements in this P n plus 1, the relation as given by star earlier still holds. So by induction, we have open sets UP defined for all rational numbers P in the interval from 0 to 1 and Q. Okay, so I'll draw a figure here so that we can kind of ground what's going on. In other words, why we just went to the trouble to construct kind of this convoluted family of open sets.
Scott?
Yeah.
I think I'm supposed to already know this, but I don't remember. So what did that bar over to the use of P or use of Q mean again?
So the closure. So think about it like this. Say I had 2 to 5, right? And this is in R. That's a subset of R. So right now, this is open. And so then if I call this A, then if I want to close it, I'm going to include its boundary points or its limit points. So closure of A would be the open set and the union of the set of those objects. So in this case, it'd be 2 and 5, which is just saying 2, 5. So the terminology is reminiscent of how we think of it open and closed intuitively. But the reason why we think about it more as this union is because it doesn't have to be an R. So then generally speaking, if I just have some open set, that is, if I take a set that's a member of the topology, then I can close it by including its boundaries, generically what it means to be a boundary in that particular space, and then just add those onto whatever. So in general, we'll find that A will be a subset of its closure, but that the closure is not necessarily a subset of its A. So whenever you see that bar over an open set, that's saying, okay, take that open set, but then just like fill in the boundaries. So that you're including now all the edges.
Yeah.
Okay, so here's what we just constructed. So all that kind of jargon is taking a look at, suppose I have a space. This is X. And this space is normal, which means that if I take closed subsets, disjoint closed subsets, then they're going to be or open sets that are disjoint from each other. Now what I'm gonna do is I'm gonna throw in here. So here's say A. It's closed, and suppose this over here is B. They don't have to be this far away from each other, but they'll just make drawing the, the open sets a little easier.
Circles within circles.
Yeah. And so the first step, remember, was we're gonna say U1 has to be the complement of the whole space with B. We're gonna poke a hole in it. We're gonna say U1 in general is X without this. Okay, so that's now gonna form an open set. A is contained in that open set. And because A is contained in that open set, we're guaranteed to have by normalcy an open set that we are calling U0 that contains that. Okay. Now that we can choose some sort of any kind of sequence of the rational. So let's just choose the standard arrangement. So we can choose for P, we can start 1, 0, that's what we've done. So U1, U0, and then we can just go down to like 1/2, 1/3, 2/3, 1/4, 3/4, and then you go into fifths, right? 1/5. Okay, so that we if you're borrowing from this sequence. So right now we have 1, we have 0. And now for 1/2, I can have some open set that still has to contain, all these guys, but it will be a little bit bigger. So I could have some open set, and this will be U1/2. And then why is it in between U1 and U0? Well, because we're operating under this relation. Think of the order relation where if P is less than Q, like so if the subscripts themselves, compare the subscripts to each other, if they're less than each other, then that tells me something about who's containing who. That means I need my closure of P to actually fit inside of the open set U sub Q. So here we see that U0, 0 is less than 1/2, which means that this subset its closure needs to be contained inside of this one. And so now this is just going to be true as we march down the list and create all of these open subsets. So we have 1/2 down, what about 1/3? Compare 1/3 to 1/2. Is it less than or greater than 1/2? It's less than. So that means 1/3 less than 1/2, okay, that means the closure of U of 1/3 that I'm about to make needs to be contained inside of the one with 1/2. So I will have something inside. I'll be like here. And it could be anything in there. So U 1/3.
So now we're going to cover.
Right. And so now we can just keep going. So 2/3, how does that relate to what we have right now? 2/3, is it greater than or less than 1/2? It's greater than. Okay, so 1/2 is less than 2/3. So that means the closure of that needs to be contained inside of this next one. So if I did 2/3, it's going to extend out even more, right?
So are they allowed to overlap one on top of the other, like, or do they have to be strictly subsets?
Yeah, strictly.
Yeah, strictly subsets.
So I'm supposed to remove that line under?
Oh, the closure is basically just making sure that your boundary points are also contained inside. So you don't want to have the boundary points missing from the
I mean because we have contained in or equal to, right?
Yeah, so in this case,
We could replace it.
Yeah.
With strictly contained if we wanted to, but it's not.
Okay.
oh, you're okay, yeah, that's just the generic subset. Yeah.
Sorry.
But then this now happens an accountably infinite amount of times, where we can just all the way down through with rationals, and it's kind of alternates. So as you change the denominator, sometimes it'll just come back, and then you'll count out, and back, and count out. But the important part is none of this includes B. It's all just around and containing A and all of these family of open sets. So this is our construction of open sets that we'll use to then talk about this function f. The only caveat that we need to do before we can do that is essentially make an extension for values that are past 0 and 1. Because right now, this is we're taking it where the elements of P have to be between 0 and 1, but we need to talk about R so that we can generalize to AB. And the way we're going to do that is essentially add two little conditions here. So we've defined UP. Now that we have defined UP for all the rational P in the closed interval 0 to 1 specifically, we extend this definition to all rational numbers. All rational numbers P and R by defining. So I'll just assign the open set empty to UP in the case where P is less than 0. So if I'm dealing with something negative, that's like, think about it in the comparison of the relation that's less than here. Let's just make it empty, it doesn't do anything. And then if UP, we'll assign that just the space itself if we exceed 1. So if we exit our little interval, regardless of what that is, we'll either just nothing or include everything. And then it is still true. We do that to preserve the order relation star. So it is still true that star holds with this extension. Okay. So now we can move to, and this is my favorite part of the next step is my favorite part. Because it's actually just a really, really genius idea. I can see why it was not counted as a trivial exercise to the reader. Okay. I know I skipped the step 2 was that little extension thing. Given point x and x, let us define q of x to be the set of those rational numbers p such that the corresponding open sets use of p contain x. So what we're saying is I have q of x is rational numbers p, x is contained in here. This set contains no number less than 0, thanks to our handy little extension where we chopped all this off. Since x in UP for since there are no points for which p is less than 0, and it contains every number greater than what? Again, because of the extension, since every x is in UP for p greater than 1. Because that's where we just start assigning x over and over again. Okay, so therefore, Q of x is bounded below. And we'll take advantage of this. Because that means that's the greatest lower bound. And its greatest lower bound is a point in 0, 1. So we'll simply just assign what that greatest lower bound should be. So we'll define f of x to be the infimum or the greatest lower bound of q of x. So now we're going to talk about we have f function f, and then this needs to be continuous with the property. So we show, it's actually easier to show the separation thing where you can assign to both sides of the interval. We show that f is the desired function. That is, it is continuous with the property that you can separate. If we choose some point in the closed subset A, and think back to that picture we drew, then that means x is going to be in UP for all the rational numbers p is greater than 0, because even starting at 0, x is in there. So that the way we define the q of x will then just be, so equals a set of all non-negative rationals. Of all non-negative rationals. And so that causes us to be able to say, well, the infimum of that, so f of x, which is the infimum of q of x,
So what's
is
infimum?
0.
Sorry, I don't think I know what infimum is.
Oh, greatest lower bound. Okay, so a lower bound. Say you have the set A, B, this is a subset of R. Okay. Now we can take things that are lower than, I should use real numbers. That's weird. Okay. 2, 5. We'll use this again. So what we're gonna do is we're gonna collect all the things that would be considered underneath this. So like -1. Well, that's a lower bound on that because it's less than all the points in this interval. So is 0, right? Because 0 is a value that is less than everything that's in this interval. But then the real question is, as I continue to collect, all these different types of lower bounds, one of these there's gonna be a biggest element in this set. So this is the set of all the lower bounds, and in that set of lower bounds, there's a biggest one, the greatest one, and that's going to correspond with obviously 2, right? 2 is still the lowest. 2 is not in this set, but it satisfies being less than. But there's no way I could choose an element that's any greater than this that still satisfies the property of actually being a lower bound. So it's the greatest lower bound. Right? So it's kind of like a stronger idea of minimum per se. You can make on an interval. Yeah. So that's what we're claiming here is that I can collect together all these non-negative rational numbers. And then if I think about that, okay, that set has a smallest, has basically the greatest lower bound, which is 0, because 0 bounds it below. And that's about as big as you can get before you start having not a lower bound anymore. So that is the inferior. Okay, and then similarly, if x is now in B, then if I have some point in UP, then for no P that is less than or equal to 1, given the nature of that we poked the hole out first with B, so that the only way we're actually getting an inclusion of something in B is if we just go all the way back to the complement. So that Q at X consists of all rational numbers greater than 1. So then f of x is 1, because then that's going to be the greatest one bound. That's it. Okay, so this is the easy side, because we've basically taken the property where f of x needs to go to a, or the bottom part of the endpoint, if you take it from a. So it's like, here's my interval. We're talking about 0 and 1, but generally this will extend to a and b. As we've taken in the space a, b. And under the function, we're going to take all the points that are in here and send them here, because of because of the way that the open sets are, and then that greatest lower bound is what we're assigning to. And because this is going to be in the complement, we're just auto sending all of those to there. And that's going to happen through this mapping F. And so this map exists because we're going to guarantee to have these rational numbers existing in our cosintervals. So the trick is going to be showing continuity. And continuity means, all right, we have the open sets, but now we need to restrict an open neighborhood or some sort of an open set that is also contained inside of an open set in R, so that we have inverse image of open to open, and then it's continuous. So we'll continue step 4 here. So we now show continuity. Continuity, we first prove, because this will be handy later, 2 facts. First, if I take a point in the closure of U sub R, then that means that that infimum is going to end up being less than or equal to R, by the way that we choose that. And then if a point is not in an open set, and that tells me, okay, then that infimum actually needs to be, we found the wrong set. We need to search for one that's past it, so it'll be greater than or equal to that R. So to prove 1, we note that if X is in the closure, then X is in just the open set as it is, or whoops, this is in some U sub S for all the values S that is greater than R. So we're basically saying, if you fit in the smaller bag, you'll fit in all the bags that are bigger than the smaller bag. Therefore, Q of X would contain all rational numbers greater than R. So that by definition we have f of x, which is the infimum of Q, would be less than or equal to R. And to prove 2, it's a very similar idea. Note that if X is not in U sub R, then X is not in U sub S if S ends up being less than R. Therefore, or thus, Q contains no rational numbers less than R. So that f of x ends up being greater than or equal to R. So now we can prove continuity. we prove continuity of f. So given the point x naught in space x and an open interval CD subset of R containing the point f of x naught, we wish to find a neighborhood which will be open U of the point x naught such that the image of this neighborhood is a subset of this open set. So we choose rational numbers P and Q such that C less than P less than f of x naught less than Q less than D. And we assert that the open set U is going to be the complement of UQ with the closure of U sub P. And that this is the desired neighborhood of x naught by construction because that's a closed set. So the idea here is I've got a closed set, the closure of U sub P, and then outside of that is x naught, which is then in turn still contained by the next one, U sub Q. And then through the map F, I'm going to take this onto R, where I have C and D with this P and Q containing the infimum of that. So first, so the space in between the dotted line and the closed set is the neighborhood that we're going to be talking about. That's going to be the open set that gets us over. So first we note that.
Oh, are you changing this from 0 to 1 to be any two numbers?
Yeah. So this can be generalized. X naught in U. And then for the fact that f of x naught is less than Q implies by condition 2 that x naught is in U sub Q, while the fact that f of x naught is greater than P implies by the first thing that we kind of proved that x naught would not be in the closure. So basically stating the obvious once you draw the picture. It's going to be in the complement between these two things, but it's greater than Q, so that means that this is still going to be contained in this point is inside of here, but not inside of the closure of the smaller subset. Second, we want to show that the image FU is a subset of this open set CP. So we'll let X be in U. Then X would be in the in UQ, just a subset of the closure UQ, so that f of x is less than or equal to Q by 1. And x is not in the closure that leads to P, so that X is not in U sub P, and f of X is greater than or equal to P by the second condition. Thus, what we have is f of X is going to be always contained in PQ, which itself is a subset contained inside of the open set CD as desired.
So it's interesting because at the beginning you did the complement of B, and so that got you real close. But on the A, I thought, well, we're going to have to do the complement of that to get real close, but you didn't have to. You could just do it because you're using the infinite. That's the clever.
Well, then, yeah, I like the ordering. So then you don't need the rationals at that point. It's just a standard index that is ordered in R. Yeah.
Nice.
It's a fun one.
Don't
So,
remember that one.
yeah, well, okay, it's probably because it's used to prove there's then the Urysohn metrization theorem. So that's probably what you did do. When that's basically saying if you take a regular space, so we don't require it to be normal, but then impose a countable basis on it, then it'll be metrizable. And so it's a way that you can construct metrizable spaces with starting with only regular separation. So
Cool.
cool. It's ticking off next week. We're finally on track again.
I don't think I understand. Just allow